Today I'm going to do a spectroscopy free response question. This was number 1 from yesterday's free response question assignment. Okay, so in this problem, we're given that a student has 100 decimal point milliliters of a 0.400 molar copper sulfate solution. And the student needs to make 100 milliliters of a 0.150 molar copper sulfate solution. And part A says to calculate the volume of 0.400 molar copper sulfate required for the preparation to make that. So we have a more concentrated solution. We need to make 100 mils of a less concentrated solution. So this is a dilution problem. So we use our handy dandy M1 V1 equals M2 V2. So M1 V1, this is the molarity and the volume before dilution, and M2 V2, that is the molarity and the volume after dilution. All right, so now we're going to just substitute in. So before dilution, we're using this solution, so our molarity is 0.400 molar. The volume before dilution, you might be tempted to put in 100 milliliters, but that is not what you need. This is just what you have. We're going to use some of this to make 100 milliliters of this. The volume that we are going to use is what we're looking for. That is V1. Equal to what we need is 0.150 molar, and the volume that we need is 100 milliliters. Whoops, I forgot my unit. So now we do the math, and we get that V1 equals 37.5 milliliters. So that is how much we need of the 100 milliliters in order to make the diluted solution that we need. So I think that might be the problem. You might be tempted to put 100 in here, but you're not going to use up all of your initial solution. You're only going to use some of it. All right, then the question gives you a list of laboratory equipment, and it says to briefly describe the essential steps to most accurately prepare the 0.150 molar copper sulfate aqueous using the equipment listed. All right, so the clue here is we want the most accurate preparation of the solution that we can have. So physically, how are we going to make that solution? We know we need 37.5 milliliters of the more concentrated solution, and we want to end up with a volume of 100 milliliters. So if we look at our list, we certainly need the 100 milliliter volumetric flask to make our solution in. A volumetric flask, remember, has a single calibration mark. If we draw it, we have a long neck, then it bulges out, and then we have a single calibration mark. So for our final solution, we need the 100 milliliter volumetric flask. Now, what do we need to dispense the 37.5 milliliters of our stock solution? Okay, so we don't need the balance or the weighing paper. If we had a solid that we were going to use to make a molar solution, then we would need that, but we don't. We don't need the centigram balance. We don't need weighing paper. Okay, the funnel we might need. The 10 milliliter beaker, the 150 milliliter beaker, we need to most accurately measure that 37.5 milliliters. So we certainly don't need beakers for that. So we have a choice. How are we going to measure out the volume of our concentrated solution? We could either use the 50 milliliter graduated cylinder or the 50 milliliter burette. Which one of these gives the most accurate volume? And that would be the burette. The burette is good to 2 decimal places And the graduated cylinder is only good to 1 decimal place. So you could certainly use a 50 milliliter graduated cylinder to make a molar solution, but we want to use the instrument that's going to give us the best measurement, the best number of sig figs. So right now I'm just going to do a little review of a burette and how we measure volumes with a burette. All right, so remember that a burette is a long glass tube, and then we have some kind of stopcock that opens and closes it. The important thing about our burette is that the calibration starts at 0, and then we have our numbers at every 1 milliliter. And this goes all the way up to 50. There are 10 intervals. So our volume, our instrument, if this is 1, then each tick is a 0.1, and in between the ticks goes to the second decimal place. So our readings give us 2 decimal places. So the way the burette works is that when we have a 50 milliliter burette and we fill it up to the 0 mark, we do not have 50 milliliters. That is just some amount of solution. It's over 50 milliliters that we have. To get a reading of your burette, you need an initial burette reading. The initial burette reading. And a final burette reading. All right, and then we have whatever we're going to be dispensing our solution into. There we go. Okay, so we need to fill our burette, and let's just say we fill it up and it's at 1.00. So our initial burette reading, 1.00 milliliters. We need to get 37.5 milliliters into our burette. So we're going to open the stopcock, and the solution is going to go down and into our volumetric flask, and we'll stop it at 38.50 milliliters. So that means that the difference between where we ended up and where we started with is the amount that actually ended up into our flask. So that will give us 37.50 milliliters dispensed into our flask. Okay, so that's why this is better than a graduated cylinder. Okay, so it says to briefly describe the essential steps to most accurately prepare the solution. So we picked the material that we need, and we could pick the funnel to help us put the more concentrated solution into the burette. So our steps would be something like this. Dispense 37.5 milliliters of the 0.400 molar CuSO4 solution from a burette into a 100 milliliter volumetric flask. Okay, and then after that, then we are going to use distilled water. So then we will add, so this is 1, 2, we will add distilled water to the volumetric flask. I'll put 100 milliliter volumetric flask. To actually what we should do to below the calibration mark. And then 3, we would use an eyedropper to get our solution up to the calibration mark. So 3, it doesn't say the eyedropper, so we probably don't have to add this, but this is what you really would do. So use an eyedropper to bring the volume to the calibration mark. All right, and that is how you do a dilution most accurately. Okay, so that was part B. Now, it says, for our next part, the student plans to conduct a spectrophotometric analysis to determine the concentration of Cu2 plus aqueous in a solution. The solution has a small amount of cobalt nitrate, cobalt Roman numeral 2 nitrate, present as a contaminant. Given the absorbance curves for Cu2 plus and CO2 plus and Cu2 plus. So this is what it looks like, what they have given us. Just put that up there. So we have a plot of wavelength versus absorbance, and we have 2 curves. And we're going to use this to answer the question. So our question says, the spectrometer available to the student has a wavelength range of 400 to 700 nanometers. What wavelength should the student use to minimize the interference from the presence of the cobalt 2 plus ions? All right, and I am going to give a detailed explanation of this. Instead of going right to the graph, I'm going to go over all of the steps so that you can have an idea of why this question is being asked and how the graph is going to help us answer the question. Okay, so what is the student's ultimate objective here? Why is the student using that graph? What does the student want to do? So the ultimate objective is that the student wants to find the unknown molarity of a copper sulfate solution. That's what the student wants to do. Now, copper sulfate, we know we have copper ions and sulfate ions. We know that Cu2 plus aqueous makes the solution blue. We get a blue solution. Now, to find unknown molarities of a solution that has a color, spectrometry, UV-vis spectrometry, is a good way to go. So that is what the student wants to do. How is the student going to do that? To figure out this unknown molarity, the student needs to make a calibration plot using known molarity solutions. Okay, so what would that look like? So that would be a plot of concentration or molarity here versus absorbance. So these molarities, and I'll just make up numbers here, maybe 0.05, 0.1, 0.15, 0.20, 0.25, etc., etc. So how would we get the data for this type of plot? And this is the molarity of the CuSO4. So we would use a spectrometer. And here's how that works. So in our spectrometer, we start out with a light source, maybe some kind of light bulb. We have a light source. And when we turn it on, we get light of all different wavelengths. So that light then goes through what is called a monochromator. Maybe it's monochromator, I don't know how you pronounce it. So when this light with all these different wavelengths comes into here, our monochromator, we have to select a wavelength. So our monochromator outputs a single wavelength. And so we have light that comes out. And we're going to make this. So we have a lot of light coming out, but it's at one wavelength. Now we have our sample, and that's in a cuvette. Sometimes they're square, sometimes they're like a test tube. And here's where we have our copper sulfate. So the single wavelength light comes in, the copper sulfate absorbs some of that light, and less comes out because some of the light is absorbed by the solution. Then we have a detector, and the detector either tells us the transmittance how much of this original light makes it through the detector, or it tells us the absorbance, how much light doesn't make it through the detector. So to get our plot, we put in a solution of 0.0500 molar, and the absorbance will be displayed on the detector, and we plot that, whatever that absorbance is. Then we empty out the cuvette, put in some of the 0.10 molar copper sulfate, and see what our absorbance is. And it will be higher because the more copper sulfate, the more of this light gets absorbed and the less makes it back out the other side. Then we empty it out, put in the 0.15, measure absorbance, empty it out, put in the 0.20, measure our absorbance. And if we've done our experiment and made our dilutions, we should get a nice straight line. It's experimental, it might not be exactly a straight line. And then we draw a best fit straight line through our data points. Okay, so now we take our unknown sample, I'm trying to figure out the molarity, empty this out, put in some of our unknown, figure out, see what the absorbance is, get the absorbance of our unknown, so I don't know, maybe it's right here, so this is our unknown. And we just draw a straight line over to the graph, not to a point, to the straight line, go down, and that is the molarity of our unknown. So that's what the student wants to do. However, we got to figure out this. What wavelength should we use? Because solutions absorb differently at different wavelengths. How do we pick the wavelength to even set our spectrometer to? That's what this question is really asking. So let's go back and look at that graph that they gave us in the problem. So what they don't tell you about this graph is that these were not done at the same time. They figured out the graph for the cobalt and then the graph for the copper. Now here our x-axis is different. It is the wavelength that is being changed, and we're still measuring the absorbance using the same instrument. So what is different now is that we're going to put one solution into our cuvette, and then we will select a wavelength, measure the absorbance, change the wavelength, measure the absorbance, change the wavelength, measure the absorbance. So before we were changing what was in the cuvette and we were keeping the wavelength the same. Now to select our wavelength, we're going to keep the solution the same and change the wavelengths. So first we're going to put a solution of cobalt 2+, the cobalt +2 nitrate, and we would use something that we know what it is. We would make up a cobalt Roman numeral 2 nitrate solution at a certain molarity, and we know what it is. All right, and then we vary the wavelengths, and then we plot it. So according to this, when our monochromator is at 400 nanometers, there's no absorption. All the light goes right through. Everything that went in comes back out. If we move our wavelength on the monochromator to 450, now the cobalt is absorbing. We go up here, so maybe that's about 0.25. So our solution is absorbing at 450 nanometers. At 500 nanometers, with the same solution of the cobalt, Roman numeral 2 nitrate, now we have our max absorbance. At this wavelength, we have the most absorbance of the light that goes through the sample. So that would be 0.5. As we continue to change the wavelength, now the absorbance goes down. At 600 nanometers, our cobalt is still absorbing, a little bit at 700, and by about 770, 780, the cobalt doesn't absorb at all. All of the light at this wavelength goes right through the sample, and nothing gets absorbed. All the light gets transmitted. Okay, so then we empty out our cuvette, and then we put into it a sample of some copper sulfate. And we do the same thing. We start at 400 nanometers, all of the light goes through. At 500, just a little bit of the copper ions are absorbing. And then at 700, even more are absorbing. And let's see, around 850, we have the maximum absorbance for the copper ions. So when we are doing an experiment, we want to pick the wavelength where we have maximum, or at least a pretty good amount of absorbance. So since we have a sample of copper sulfate that has some cobalt in it, we need a wavelength where the copper absorbs and the cobalt doesn't. Because if we have a wavelength where they're both absorbing, it won't tell us the molarity of the copper. It'll tell us it doesn't tell us that anyway. So now they're telling us that our instrument has a wavelength between 400 and 700 nanometers. So that's what we're limited to. So what would be a good wavelength to pick between these two? Well, we want to pick somewhere where the copper is absorbing and the cobalt isn't. The best place is right at 700 because we've got a good absorption of the copper and a very low absorption of the cobalt. So the cobalt will absorb a little bit. It's not ideal, but the copper will be absorbing much, much more. If we had an instrument that went up to 850, then we could pick 800, because at 800, only the copper absorbs and the cobalt impurities in our sample won't have an effect. So the answer to this question is 700 nanometers. And by the way, this is the range of visible light from about 400 to about 780. So this is the red light end of the spectrum, and we go in Roy G. Biv order down this way. So this is the red end, this is the violet end of the spectrum. So copper is a blue solution because it absorbs strongly in the red. What we see is the opposite. color of what is absorbed. The cobalt is a pink solution, and that's absorbing here near the blue end of the spectrum. So this question is for what wavelength we want to use to set our instrument to in order to make our calibration plot, in order to figure out the unknown molarity of our sample. That's it.